Good morning, everybody. Today is the day 5. We have Dr. Manohar Lal Munjal from IICTE Bengaluru. He is a professor, and he will be speaking about the noise reduction in machines, or adolescent talent. Okay? So interact with him. If you have any queries, discuss freely. Don't be hesitant. Next, I'll hand over the session to Dr. Manohar Munjal. He will be continuing the session.
Thank you. Good morning, friends. So, as you have just told that this is the fifth and the last of this lecture series, and I'm trying to actually give you really the gist of what all we have been trying to do, and for you, of course, it will be the start actually of your learning noise control. In fact, I was telling that control that they should get a couple of copies of my book in the libraries. And of course, because now that Indian edition is available, all of you study vibration and noise, you can buy your own books. Now, basically, I'll be testing the fundamentals, but more than that, the real stress is on applications. So therefore, feel free to ask later if something you would like me to repeat. Your noise may be controlled at the source, in the path, or at the receiver end. So please try to always understand always in any new situation, you have to ask, noise is coming from there, so can I do something right there? And finally someone is getting disturbed there, can I do something on the way or in the path? If I cannot do that, can I do finally to help that person to hear response? So these are three approaches, and remember one thing, the nearest, anything you do nearest to the source is the most effective, most cost effective. So really, if I can do something right there where the noise is coming from, it is the cheapest and most effective. But once it spreads, then I'll have to do everywhere. Obviously, whatever I do is going to be much costly. And third, of course, is finally, if I can do something there, it will be good only for that person, not others. What I am trying to say is effectiveness goes on decreasing as you go away from the source. So as engineers, our first thing should be, can I do something right there? Okay? So the noise doesn't come out of that place. And that is my stress, and that is what I mean when I say designing for quietness. You design the machine in such a way that there is no noise produced, that's the best. Once it is produced, you will have to spend much more time and money and effort to control it. Now, designing for quietness is the most cost-effective way. As they say, prevention is better than cure. Now, in this lecture, we list and illustrate all possible techniques and strategies for noise control of an existing machine, as well as choice or design of quieter machines, processes, and industrial layouts. And as I told you yesterday also, most of this is from personal experience. As I told you, I have done 125 consultancy projects in my life, and this is what I am giving you really is the gist of what has worked. Okay, so you are very lucky to get me right directly what works. Okay, I did everything mostly by self-learning. So for me it was a hard way, but now you are lucky to get this thing ready. Now, as I told you, first thing I should ask myself, can I control the noise of the source? Noise of the machine may be reduced at the source by adopting some of the measures or practices listed in the following slide. These are titles of the next slides that are coming, but I will just read you the titles. First is select a quieter machine. So this is the best thing when I'm going to buy a machine from the market. Well, I must see that of the various machines available, I should go in for the quietest machine. And I'm also tell you later, the quietest machine is not only noise-wise quieter, it's the best thing in many other ways, because things are related. Next is, if I'm choosing materials, can I choose lossy materials, dense materials, something that absorbs energy, okay, right there where it's being produced. Use quieter processes or tools. If something can be done in different ways, okay, can I choose the way which is relatively quiet? Then reduce radiation efficiency. That means for a say plate or something which is vibrating, can I design the plate or remodel it in such a way that for the same vibration, noise is less, because that ratio is called radiation efficiency. Then maintain for quietness. This is a very important thing in India. It's not so much actually in the south, but in the north, it's a very dusty atmosphere. All the time our vehicle, when for example if I have a car, all the time the air that is inhaling, it is very dusty, and that finally settles at various points, and the machine really, starts becoming not only bad otherwise, but also noisy. That's why you'll find that a car which has run only for 6 months, you feel as if it has been running for years. In fact, let me also tell you, like things are a little better in Bengaluru with respect to Coimbatore. Yes, Bengaluru is 3,000 feet high and it's on its plateau. So the air there does not have that much dust as I find dust here in Coimbatore. Okay, but when you go to north, it is much worse. In the Gangetic plains, it's very, very dusty all the time. And this is the most important thing, design of flow machinery for quietness. Because 50% of all noise in the world is always coming from flow machinery. Fans, blowers, turbines, HVAC systems and so on. Right, so let's start the first one. Yeah, can I select a quieter machine? What does that mean? I say select a quieter machine from the market even if it is relatively costlier. Often this additional cost is less than the cost and hassle of the retrofit noise control machines. Whatever you try to do later will turn to be much costlier than spending a little extra money in the beginning itself. A machine would generally be quieter if its moving parts were fabricated to closer tolerances. This is something in India for which we are ourselves responsible, and that's why most of our machines are noisier. Because when we make rubber drawings, fabrication drawings, we unnecessarily put additional tolerance. Because we say that anyway it will go to be cheaper, because when tolerance is more, the person doesn't have to be too careful, etc., and things can be done faster. But this is standing by its own position. Because in the long run, you are going to pay a very high price for doing that kind of thing. In fact, one thing I would just like to tell you, in Germany, so I was there for 1 year, and I directed several companies. I found the tolerances typically, when you look at their manufacturing drawings, they used to be much closer, much less, much smaller than what we do here. Okay? And I also found that German machines are the quietest in the world. They spend that extra fabrication time and effort to make those machines to closer tolerances. But finally what comes out is a machine that during the life will work out to be much cheaper than it would have been otherwise. Okay, so what I'm trying to say is look at lifetime cost, not initial cost. Most of the time, we only look at initial cost and make wrong choices. So that is what should not be done. Now, manufacturing making parts to closer tolerances reduces micro-impacting within the parts. Now, this in turn reduces the mechanical impact noise, it reduces vibrations, it reduces wear and tear, increases fatigue life, increases the interval between maintenance outings, and increases the accuracy of the machine tool if that is what they push for. So many advantages we have when we manufacture these mating parts to closer tolerances. Now, continuing that same thing, overall, manufacturing to closer tolerances is a good engineering practice and makes economic sense in the long run. In other words, the lifetime cost of a quieter, though costlier, machine is relatively low in the long run. Now, human desire to obtain large power from small power packs, particularly for aerial engines, motorbikes, and automobiles, has resulted in a race for high-speed engines and turbines. However, noise control at the source can be achieved by selecting large, slow machines. Mind you, I am saying large, slow machines rather than small, faster machines. However, noise control at the source can be achieved by selecting large, slow machines rather than small, faster ones, particularly for stationary installations of captive diesel generators. Now let me explain this one. What I am trying to say is that let's say somebody is trying to design a moped. Now obviously his concern is I should have a small vehicle, small power pack, but it should give me a lot of power. So in the process, moped engines you're trying to running at 8,000 RPM. Okay, let's look at diesel engines running at just 1,500 RPM. So what I'm trying to say is that in trying to get more power from smaller packs, we really make certain choices which are very unhealthy from the noise point of view. Another thing I want to tell you is that many times, even from the mechanical engineering efficiency point of view, it's not a very wise thing to do. For example, I'll just give you some idea. Have you heard of Russell and Hornsby? Anyway, those are manufacturers of very large engines. You know, and the first time I saw, in London, an engine running almost like size of from here to there, that kind of engine. And now what this man had done, he told me later we traveled together in the same plane, and he told me something interesting. He says, he came across a ship, and that ship had been discarded, just almost thrown away in the yard. So he says, what I did was, I took out the engine from that, and this is the engine, this thing that told me. He says, this is the engine that I have been using. It runs only at 125 RPM. Mind you, 125 RPM. Now, because it runs at 125 RPM, all of you know that centrifugal forces are proportional to omega square. It means proportional to speed square. And because now speed is 1/10 of normal, actual those inertial forces will be 100 of what is otherwise. Okay? Now, the unbalanced inertial forces are 100 for the normal engine. Second good thing is that those forces act on such a big engine, the mass is so much that no question of vibration isolators, nothing at all, nothing was needed. Because those forces are not even sufficient to shake this engine, leave aside any unbalanced force going to the ground. Okay? Then he showed further, he said further, because it is running at 125 RPM, nothing can happen to it with time. Because there are hardly any vibrations, hardly any wear and tear, okay? And therefore, whatever is done once, it stands there forever. He even told me lubrication, that lubrication was done 3 months ago. That is not needed because whole thing is running so slow that, I really came to know that day, the advantage is slowing down. We are going faster and faster. Here is something very interesting this man did. And so he was telling me something very interesting, and he came to know that I am in noise control. So he was very much interested in telling me, what he did he was not in noise control. It happened. He only went as he has used what he said, my mechanical engineer's common sense. Okay. But anyway, I learned a lot during that journey with him because up to then I had not thought what speed is doing to us or what we are doing to ourselves by making things faster and faster and faster. So from noise point of view, slow down, ask yourself, do I have to make it run at such a speed? Another thing I want to tell you here is that, okay, mopeds, scooters, cars, etc., we want a small power pack, at the same time we want more power, fine. But every time even that is not there. For example, suppose I am putting a stationary compressor here, and that compressor is not running on the road, nothing at all. It doesn't have to run faster. If, for example, instead of the size of, let's say, half the table, the compressor is double the size of that table. All I am spending is maybe 10% extra on the steel cost, material cost. Okay, and ground, and this doesn't matter wherever the compressor is lying. The space cannot be such a problem at all. So unnecessarily, why should I design that compressor to run at higher speed? Okay. In fact, now let me just tell you, I have been selling this idea to defense. In our ships, etc. I've been telling them that please slow down. Let it be large engine running at smaller speed, and you will find that most of the problems that you're facing are not there. Not just from noise point of view, from wear and tear, the endurance life, and everything. And yes, so this is what I just thought I would share with you because most of the people didn't know that speed is playing a very devastating role. And therefore, as a mechanical engineer, designer, we should always ask ourselves, do I have to design it for higher speed? Why? Instead of why not, say why. And then get the right answer and proceed. Okay. Now, I was telling you select glossy materials. Now, this is a very important part. I'll just tell you here that I was telling you yesterday that I was consulted to Tata Motors for Indica. They asked me a lot of questions to start with, what will you do, nothing. I just said, listen, most of the noise is from resonance of parts. And resonance means free vibration of loose components. And I said all we do is we choose more lossy materials. We build in damping in the system. And good thing about damping is that I don't even have to know what is the resonance frequency for which I am designing. All resonance frequencies will be damped if I have built in damping in the system. So that's what all we did in the first Indica that was designed. We said we don't know yet what are the frequencies we have to worry about. But if we put sufficient damping in the car, we are in business. And that's how it happened. So I'm just trying to tell you now, mechanical impacting sets different parts of the machine into free vibration. Mind you, all the time I'm talking free vibration. Damping is not good for forced vibration. I'm talking about free vibration. The sheet metal components or covers, vibrating in the natural mode, radiate noise into the atmosphere. You might have seen, for example, if you look at an engine, though the real culprit is the high rate of change of pressure in the cylinder because of combustion. But noise is not coming from there. This excites the cylinder head. It excites the cylinder block, and then through the connecting rod it goes to the crankshaft, the bearings, and these bearings are housed in this one. The whole housing is finding what's vibrating, and that is what produces noise. Okay, so it's a very interesting thing, and so therefore all we need to do is make sure that final noise where it is coming from, those are always this kind of covers, etc., sheet metal components, and they act like mechanical loudspeakers. So if we have built in sufficient damping, we will have no problem. Okay, let's see. The free vibration of sheet metal components can be reduced by fabricating these components out of lossy materials like plastics, that is materials with a relatively high loss factor. Now, all of you do that when, we say stress divided by strain is elastic modulus. Okay? But in real practice, elastic modulus is not a real number, it's complex number. Okay? So real thing we call storage modulus, imaginary we call it loss modulus, and the ratio of the two, loss modulus divided by the storage modulus, that is called the loss factor. So basically what I am trying to say is designing for more loss factor, or that's what I mean by lossy materials. Alright. We could consider replacing metal gears with plastic gears. Of course, we have to remember that such materials are very low in strength and therefore cannot be used in high stress locations. But everywhere we don't have a stress or loads coming in. We, for example, design many things like children's toys. Okay. Now no stresses are coming there. Okay. So unnecessarily we don't have to design for stress. Alternatively, we could make use of free layer damping or preferably constrained layer damping for the sheet metal components or covers exposed to the atmosphere. For example, now there is an example, simple one. A circular saw blade should be replaced with damped blades. In fact, I will be coming to many of such examples later. Just simple things like this we do, and the problem is taken care of. Okay, now next thing is when we are choosing, we are trying to do something where there are several alternatives, and so when we choose one process, ask ourselves, is it the most widespread process? Now, one very popular way of reducing noise in energy conversion is use of electrical motors rather than reciprocating engines or gas turbines. That all of you know, we are going for electric vehicles, etc., mainly for this noise. Okay. So basically, this is the thing. I repeat that part. That use of electrical motors instead of reciprocating engines or gas turbines. Other is use of high velocity jets for cleaning must be avoided as far as possible in industry. We should seriously consider replacing pneumatic tools with electric tools and pneumatic ejectors with mechanical ejectors. This is something you must have seen if you go to any sheet metal kind of workshop. But noise will be so much that you really regret that you came into that. And most of that is all self-created. You know what they do? That is, somebody has a punching machine, so he uses high pressure air, and then he's doing like this, and taking out the parts, small things coming out, and that produces racket. In fact, when I first time was asked to silence that kind of workshop, I tried to go to everything. How they were doing, why they were doing, etc. So I had almost 4-hour session, the foreman, why he chose particular machines, why he chose particular processes, etc. And then it's very easy, just the compressor is there, you just take that thing and use it, and it will get parts. I said, how did you feel the pressure of the compressor? No, it was already there. This joint was there. They are fine. Now I found that it was 7 bars pressure. 7 bars pressure he was using. So the air that was coming out was supersonic all the time. And super getting shocks there, right? And using so much noise. And it was very, very bad design of the whole workshop. Because finally he admitted, oh no, we never designed it. It was there, but the work that kind of thing. And that's what is the problem in most of our companies. Whatever works, do. Never ask why. And whether that could be done cheaper or quieter or lighter, nothing. No questions asked. In other words, no designing goes into their thinking at all. So anyway, so because I'm just trying to tell you that in this case, what I always did was, I said, now listen, you go in for a compressor, giving you pressure only 2 bars pressure. You don't need 7 bars pressure. And he says, that will people have to buy it, it will be new thing. I said, no, just don't worry. Because indirectly what you are going to save, you will see how much is saved by choosing a 2 bars pressure. So all we did was, for example, if you look at the nozzle, which is using for cleaning, okay? Now, all of you know that basically thrust is proportional to mass and velocity or momentum. Or rate of change of force is basically what is the thrust. So I said, instead of having a jet of, let's say 2 millimeter diameter and giving you velocity so high, you choose just instead of 2 millimeter, make it 3 millimeter. So I have increased the mass now, and then velocity is decreased. Okay, and then when you find the thrust, thrust is still the same, but noise is proportional to 8th power of velocity. Noise is proportional to 8th power of velocity. So if I have made the velocity half, I am reducing the noise by 24 decibels straight away. So all I did was I designed for them the new nozzles, everything new. I said now forget about, just don't worry about the cost, and then you do it. And when they did that, you will be surprised. The all extra costs, including compressor, everything, and nozzles, everything put together, was just 2 lakhs of rupees. Okay, and they had to give me 5 lakhs per consultancy. So what I'm saying is that that 2 lakhs was nothing with respect to what otherwise they would be. But then it was very interesting later that the manager and everybody became friends. So they were saying, what we are doing, please don't mind it. We are using all your knowledge to design other workshops for our other branches. That's great. So we have saved so much there because everything we designed, taking that into account. So what he was trying to say that even the 5 lakhs that we are giving you as consultancy is also no problem because we are already using 5 times at 5 different places the same knowledge. Now this is, please try to look at forging down to the net shape in a single step die is another source of high dies in workshops. We must consider replacing single operation dies with step dies and rolling or forging with pressing. So this is what I was saying, when the user quieter process, the same thing you can do in so many ways. Okay? So this is one. Like for example, I'll just tell you here. Now let us say I want to put a name here. One is that I take a hammer and do it. And imagine how much noise will be there. In the second one, I just hold that nail in this one drilling machine, you can see, and then just I go on pressing and forcing goes in very little noise. But of course, drilling noise can be there, but then that's a different thing I'll come to later. But what I'm trying to say is, if you want to bend something, instead of bending it just with again hammering, you catch it, then you do it like this. Same thing you can do, no noise at all. So at every time, whenever you want to do something in your designing of the machines and processes, ask yourself, this is the brightest way of doing it. If not, can I do it this way? Can I do it this way? So all the time, in fact, in actual practice what is done is, all designers are supposed to keep certain design tables with them. Okay. For example, if something has to be done, it can be done in this by this process, this process, this process. So all processes are listed. So when you are designing, before choosing one of them, you just mentally go over it with respect to noise. What will happen to it? Or cost, etc. Everything you can do. So always have the alternatives in your mind when you are designing. And that is what now I was telling you yesterday. Most of the books that have my copies that have been sold, they have been bought by companies. Okay, and now I have told them, and they have taken that advice that every engineer will have a copy of my book on the table, because it gives them all those choices. They can ask that question when they're designing. Everything of course one cannot remember, they don't have to remember. So just go to that particular chapter, say, okay, well, these are the 7 things, which are relevant to this. Can I select this one or this one or this one or what? And this really helps. Alright. So here I am saying that when you are forking through some shape from some shape, instead of doing it in a single die, okay, you use step dies that shaping is done in steps, and everything will be quieter than otherwise, and total noise will be less. Next is increasing the contact time during impacting reduces the rate of change of force. Therefore, rotating shears produce less noise than mechanical presses, which in turn are generally quieter than hammers. Similarly, welding or squeeze riveting creates less noise than impact riveting. So basically what is being said is the contact time and the surface, not only of time. Now what happens is when I am hammering, if I am using, let's say, its anvil is this steel anvil, and then my hammer is also steel, and when I do like this, the contact time during which hammer is on the anvil is very, very small, and therefore it's very, very noisy. But same thing, if I could change the surface in such a way that it stays for, let us say, almost half a second, you will feel there is no noise at all. And same thing is about the contact area. If I can increase the contact area, that power transfer that is taking place, that will go to the larger area, and that will be much quieter than when the contact area is very little. I will just show you. Here, I am saying the rotating shears produce less noise than mechanical presses, which in turn are generally quieter than hammers, all because of this contact time. Similarly, welding or squeeze riveting creates less noise than impact riveting. In fact, particularly if you have seen sometimes in the aircraft industry, and how that those things are there, putting those various plates together to release riveting. Or if you see, for example, any bridge being built, so you will find how they do it, and everything can be much quieter. Otherwise, they will make their own life happen. This is what I was telling you. Earlier I talked about less contact time. Now I am saying more contact area to make it quieter. So I am saying increase the contact area. How do we do it? Increasing the contact area is a potent method for reducing noise at the source in material handling. Therefore, use of belt conveyors instead of roller conveyors recommends itself. For the same reason, helical gears have been observed to produce much less noise than spur gears. And spiral cutters are quieter than straight edge cutters up to 10 decibels. So you can see in spur gear, just the contact is just like this. So it's only this much. But in spiral gears, scope is going like this. So the contact area is much more than in the spur gears. Now probably the best example of noise reduction by increasing the contact area is use of belt drives in place of gear drives. All of you know that, belt drives are quieter than gear drives, mainly because of this reason, that the contact area in belt drive is more. As a matter of fact, also pneumatic tires instead of solid steel wheels. You can imagine now, like the railway wheels with the steel moving on steel. and therefore the contact area is very difficult to contact that area. Whereas same thing in our automobiles, we are using tires and the contact pad area is so much, and therefore it is much wider than the corresponding area. As a matter of fact, development of pneumatic tires made of rubber and nylon strings was probably the most important step towards reducing automobile noise and preserving the pavement. As you know, it's true. When I was at Ford Motor Company, I heard a story. The first time Henry Ford, when he took his car out on the road, firstly, of course, it was the first time anybody was seeing the car. Nobody had seen the car at all. Okay, and this poor fellow, Henry Ford, he had made it in his garage. So, and there was nobody to guide and all by himself, single person, everything big. Okay, so of course, first thing itself was when the car was ready, he could not take it out because he had not thought of that how he finally take it out. So one side of the hole, that thing had to be broken so that this could be taken. Second was, naturally he had not thought of 100 things that happened later. He had not put pneumatic tires. Okay, it was a normal steel wheel. And then of course the other thing was that because everything else was also like that, it was very, very noisy. So noisy that whole of the town, everybody came out of the house thinking that some monster has entered the city. That was the first reaction, that is a monster, because they had never seen a big machine moving by itself, So that itself, then it was, everything else was so rough, so noisy, that it became like that. Anyways, what I'm trying to say is, now we take it for granted, everybody uses rubber wheels, okay? But at that time, it was not known. So I'm just saying, as a matter of fact, development of pneumatic tires made of rubber and nylon string was probably the most important step towards reducing automobile noise and also preserving the pavement. So it was very interesting. The road on which we took that car completely spoiled the pavement. Because that road was gone. Yeah? Because this complete, the kind of contact that was taking place, those roads had not been designed for that at all. It was the first time such a thing happened. So in fact, it also became an issue, that people wanted to pay for that road. So Henry Ford had to face a lot of problems, not non-technical kind, that he had to pay for everything. Okay. The next thing I was telling you, that I said reduce radiation efficiency. That means, first thing is, of course, we should make sure that vibration should not take place. Second is, if vibration is taking place, then you design that plate or whatever is radiating noise in such a way that radiation efficiency is less and the noise should be less. Let's see how we can do it. For a given vibration amplitude, noise radiation from a structure depends upon radiation efficiency, which in turn depends on the shape and texture of the vibrating surfaces. Now, flat, continuous plates are efficient radiators of sound and therefore must be replaced with curved or ribbed panels, perforated plates, or woven strips of metal. Number of things I am telling you: curved, or ribbed, or perforated, or woven strips of metal. Two sides of a plate radiate out of phase waves and perforations expose both sides of the plate simultaneously, resulting in substantial cancellations at the holes or periodic gaps. This effect roughly represents conversion of monopole mechanism of noise generation to dipole mechanism, which has intrinsically much lower radiation efficiency. I am not taking to monopole, dipole, etc. But all I am trying to say is that just look, I'll give an example of this table again. Suppose this table is vibrating. Whole of this surface, is pushing the air together, pushing out, then sucking in, pushing out, sucking in. So this is what becomes the radiator surface, similar to like the diaphragm, that kind of thing. Now, if I put holes in this, what happens is that when this is vibrating, other surface is also vibrating and out of phase, because when this upper surface is going up, other surface is going, this is sucking. This is pushing the air out. This is sucking the air. So noise produced with the upper surface, that is out of phase, with noise produced by the lower surface. And because of holes, they are both acting together, and what net result is there is silence, literally silence, the particles of this surface like that there, because they are getting compression wave here, reflection wave here. Net result is at this point there will be nothing. So what I am trying to say is this is a very good way of cancelling, that we should make sure that we should use perforated surfaces wherever we can. Now let me tell you where you can. I will give you one instance which you all of you are very familiar with. You might have seen on the railway platforms, the trolleys are there, and in the trolleys those baggages, they are taken. And the trolley, moving on a platform, you know how much noise it makes. All of you, particularly if no suitcases are there. Okay. Now, we don't have to use solid surfaces there. But basically, we use moving bags, suitcases. So we don't need solid surface. So make it, perforated surface. You save on material. At the same time, you find the noise from there will be much less than other noise. Similarly, let me give you another example. Let's say you have a compressor, engine running a compressor, okay, and you have this, their shafts are coming like this, you have the coupling here. Now, this coupling can be very, very risky, so people have to be protected from that just in case something happens. So you want to make a cover, and that cover doesn't have to be solid. Make it of a perforated plate, mesh. Mesh is good enough because all you want is mechanical protection. Okay, and then you will find there is no noise at all. So, that's why I am trying to tell you, my whole way of writing this book is giving you the options all the time. And then you as mechanical engineer just use your common sense and make use of the right options every time. And that's it. Now use interwoven metal strips. This is a very interesting thing I want to share with you, because I also did not know when the first time when I encountered. And I was telling you that I was there for 1 year in Germany, and then from there I was invited by University of Southampton, England. Okay, I went for give 2 or 3 lectures, and that Professor Davies, who was my post professor, he took me somewhere, and to show something, and then this idea I saw for the first time, which I am telling you here. Interwoven metal strips, very interesting. This mechanism of noise reduction can be and often is utilized in design of hoppers, stillages, or tote boxes for material handling operations. Often the noise in a factory is increased dramatically when the metal core, castings or waste materials is stripped into a tote box made of sheet metal. If this tote box or stillages are made of interwoven metal strips, noise reduction of the order of 20 dB could be obtained. And this professor showed me here got reduction of 26 decibels by using this thing. This represents a tremendous noise reduction and the source at minimal cost. This principle can also be applied to cover transmission couplings, baggage trolleys on railway platform, side covers of mechanical hammers and presses, etc. Now, let me explain a little. Basically, I'm talking like this. You have basically things like this. So you have one set of strips coming there. Other like typically we also use for cords, etc. Nivar and pets. Okay. So now, if you do that now, and you are doing a number of things. One is that I was telling you using the holes, etc. So basically, it is another version of that. Second is, because they are intertwining all of them, every time this moves, this also moves, and the relative motion is there, and then damping comes. So you are making use of the fact that we don't have a solid surface, you have strip surface. Then you also have the strips, they rubbing against each other and having damping, etc. So everything put together, 26 decibel noise reduction. And I was telling you yesterday, 10 dB noise reduction means I have reduced the noise to half. 20 dB means half of half, that means I have reduced to 25%, and so on. So 26 dB means almost like 20%. So 80% reduction has been got. We have only 20%. And now, after coming from there, just 2 years later, I was invited as a consultant by EHL Fisher. And it was eye-opener for me. Those of you, is anybody from Fisher here? Okay, what I'm trying to say is that there are two BHL factories there. One is the boiler side, that factory, and other is making seamless tubes. Seamless tube is very interesting. The whole thing is done in a number of processes, and finally this 6 meter long tube comes and falls into a tote box. And now tote box is simply they have made it like a bar, not a bar, just like this, all made of plates. So when this falls into that, all the surfaces of that tote box, they act as such big loudspeakers, and it's happening all the time because their business is that. So all the time they are falling one after the other into the tote box, and tote box is really vibrating and producing a lot of noise. And another thing I'll tell you, the practical side, you may laugh at the whole thing. Those days I didn't have a sound level meter which immediately within 1 second gives me a spectrum. I had the old fashioned one. It used to take me 45 minutes on one spectrum. So if I'm taking readings, I had to stand there for 45 minutes to complete one frequency spectrum. I want to tell you here, I was much younger at that time, I was maybe 32 years at that time. I could not take the spectrum. Please understand what I am saying. I could not stand that noise for 45 minutes to complete that spectrum in that workshop. And then I felt so bad for all those people there. I said, here is me coming, could not take my one set of readings. And these poor fellows, they are working 8 hours a day for their livelihood. So because that is their job. Okay? And those days there was no audiological testing, etc. And later on when it was started again in BHL, they found that 50 to 55% of them were half deaf already. 55% were half deaf just because of no fault of theirs. They were working in that kind of noisy environment. And all they had to do was something just similar to this, leave the tote box, from strips and all that. And that's it. So I'm just trying to tell you here that, you learn a lot in consultancy, because, otherwise you can't think what's going on really in the actual factories and how people are suffering, knowingly, unknowingly, and so on. In fact, talking of this, let me also tell you something first, just for a change. Again in BHF, but not of this problem. They asked me to look at some problem, and I had another person, local person from a factory, and then we were studying that situation, and after that person went away, these people got hold of me and they wanted to ask me, what was that, why was that failure? And then, I said, we are trying to reduce noise in your environment because it's working very constant. Very noisy. And then they asked, how much will it cost? I said, I have not done the design yet. Maybe I said, at least 2 lakhs of rupees, that is what we are thinking. So you will spend 2 lakhs of rupees on this. We have been asking for a glass of milk every day, so that we can stand that noise, and they are not giving us that 1 glass of milk. And they are ready to spend 2 lakhs of rupees on noise control. Imagine now, question of ignorance and things combined. Okay, they thought that if a mechanic is given to a glass of milk, he can stand noise the whole day, nothing will happen. So I try to tell them 2 things are different. Noise is like a slow poison. It will make you slowly deaf, and you lose so many other faculties also because of that. And it is for that, No, but just tell them that we don't want them. Let them give us a glass of milk each one of us, and every day, and that's okay. Now I thought it was some kind of a joke, etc. But nothing. They were very serious. Later on, then we had discussion with the general manager, etc. And then it says, sir, we have opened a Pandora's box. You should not have told them what you are going to do, how much it will cost, and now it becomes a union problem, and they will use it, against us and all that. And I just didn't know what to say there. So what had happened. Anyway, but all I want to tell you, all of you sitting here, you are also going to industry after that. I was told later that glass of milk had to be given, irrespective of whether the other 2 lakhs is spent on noise control or not. Because that has become an issue, of that union. And so therefore that, so much so that it had to continue for several years later, and somehow finally they came out of it. Otherwise, that would spread to all the other units of BHL all over the country. Everywhere, everybody had to be given glass of milk, etc. All additional cost everywhere, and they couldn't avoid. So, that's the damage I had done by, not knowing where to talk, where not to talk. Okay? But in India, we have those kind of situations, which are very, on the face of it, non-technical, but they are as real as any technical. Okay, now another thing I want to tell you that any machine when it's new, it is relatively much quieter than a few years later. So because it's not maintained for quietness, so it's not designing for quietness. It's necessary but not sufficient. We have also to make sure that we are maintaining quietness. How do we do this? Often it is observed that a machine that has been used for a while is no longer as quiet as it was when it was first installed. In order to avoid this additional noise of the source, it's necessary to have the rotating parts of the machine balanced on site, not at the supplier. It's a very important thing. Often, when they sell you something, they say it has been not balanced. No, when it is balanced at site, there is an effective, it's not sufficient. During the transport and everything changes. Finally, when they install on your workshop, it will have so much unbalance and produce a lot of noise, and also, the wear and tear. Monitor the condition of the bearings continuously and have them lubricated regularly. Replace or adjust the bore or loose parts as soon as detected. And finally, follow the periodic maintenance schedule specified by the supplier. So this is all necessary, all AICTE. Next is, if a machine is thus maintained, its noise level will not unduly increase with use or age. Increased noise is often a symptom of poor maintenance of the machine. If not attended to, the primary function of the machine would be compromised, and chances of its failure or malfunction would increase alarmingly. Now I was telling you that this is, most of the time noise is from flow machines, and so therefore I am giving you 3 slides only on flow machinery, and they are very important. Please look at bold case. Most often, noise is radiated by cooling equipment. As a rough estimate, half of all noise in the world emanates from fans, blowers, and heating, ventilation, and air conditioning systems. Noise control of flow machinery at the source may be evaluated as follows. I am giving you various things. A. Provision of adequate cooling fins would reduce or eliminate the need of fan for forced convection cooling. Then either the fan would not be needed at all, or a small, relatively quieter fan would do. What I am trying to say is that noise is being produced by the flow, but flow itself can be reduced if the heat transfer coefficient has been increased by using fins rather than flat radiating surfaces. Now, centrifugal fans are generally quieter than propeller fans of the same capacity, working against the same backpressure. Again, backward curved blades produce less noise than the forward curved blades. And computational fluid dynamics can be used to design quieter blade profiles like air curved blades. So what I am trying to say here is that we are now trying to see that noise, low noise can be reduced if the basically the flow machinery is designed properly. If the flow entering a fan does not have uniform velocity profile or is highly turbulent, then the fan will produce more noise than usual. Therefore, we should locate the fan in smooth, undisturbed airflow, not too near a fan, for example. Continuing that, large, low-speed fans are generally quieter than smaller, faster ones. Now, this is something that I want to stress here. Often you go to these factories, you have, for example, let us say, number of layers in one row. People are working on that, and then what this management does is put a big fan here. Big, you might have seen, and then, giving air and thinking that everybody will be taken care of. Now, this is a very bad engineering for 2 things. One is that now you are using a large fan, pushing so much air and with so much velocity, because you also want large person there also to get some wind. Okay? And it produces hell of a noise. Second is that, everybody is not getting the air that it needs. I mean, you are not satisfying yourself in general way that I am putting so much of air for everybody to take it. It doesn't go like this. So what I am trying to see here is that get small fans, put small fans where each one of them, everybody has a fan of its own. Okay? And total cost, let me tell you, will be less than what you will be spending on this. At the same time, no noise. Normal fans, that table fan we have, small fan, and many times now what is done, you might have seen the industries. Fan is a part of the machine. They make sure that the fan can be fitted onto the machine, so that when a person is working on a lathe or whatever, he has a fan for himself. Small fan. Doesn't cost much at all. And no noise. Okay. Noise in high velocity flow ducts increases substantially at the sharp bends due to separation of boundary layers. Therefore, adequate CFD modeling may be done and suitable guidelines may be provided to avoid flow separation. So basically, all noise is produced when boundary layer separates or free shear layer is formed. So you have to make sure that the flow remains attached to the surfaces, and then you will find not only noise will be less, the losses that happen because of eddies, that will also not be. The flow noise or aerodynamic noise from subsonic jets increases with 6 to 8 power of flow loss. Therefore, we should design the flow duct so as to maximize the cross section of the flow stream. Incidentally, this consideration led to the development and use of high bypass turbofan engines for transport aircraft. It reduced the jet noise to 10 to 20 decibels while retaining the same thrust. Moreover, propulsion efficiency of turbofan engine is higher than the corresponding turbojet engines. You might have seen if you go. You don't have to go to the history, but maybe I just want to tell you here that mostly these engines and corresponding aircraft were developed in a hurry during Second World War. During Second World War started in 1939, ended in 1945. So within those 6 years, the kind of research and development that took place in the world was not even equal to the next 20 years. Okay? But in the process, they did so many things which were okay with respect to those at that time, in those circumstances. But they were really unnecessary or wasteful to do later. And one of these things I'm just telling here. Those days, you did not have bypass engines. You had, for example, let's say you have inlet nestless, then you have low speed compressor, high speed compressor, and then you have combustor, then you have turbine, HP turbine, and then you have the expansion nozzles and the thruster. And those were so noisy that after the Second World War, nobody thought that they could ever be adapted for transport aircraft. It was all right for soldiers because anyway the part of the war, so comfort is not considered at all. So it took about 10 years, and then somebody thought of this bypass engine. Now you might have seen anytime you go to the aircraft, you'll find that you have the central portion, the axial portion, and then you have this big fan. Substantial part of the air is not sending an engine at all. It is going around it, and then finally again it mixes at the end. And in this process, I was telling you the thrust is equal to mass into velocity, etc. So industrial scale. So you are able to get the same thrust that you want. At the same time, the mean velocity of the jet is reduced almost to 1/4 of it. So noise being proportional to 8 power of velocity, so it is reduced by about 20 to 25%. And that is what made these engines quite enough for public to accept. Although the public would any day would like to go by train, they would go by aircraft because the kind of noise was such those days. After 55, this transport aircraft became viable both cost-wise as well as comfort-wise, all because of this concept of bypass turbofan engines. And same thing, I'm also going to tell you the principle later, we use in so many other ways. Now, continuing that whole thing, design of flow should be provided. Now, drastic reduction of pressure, as in high pressure venting of air or superlative steam, in a single step, I talked about it 2 days ago. Okay, single stage expansion phase 1 produces very high sound pressure. This may be reduced by means of a multi-stage expansion fin valve or a series of adequately designed RF displays. In fact, I will show you in the next slide. The noise of a fan or blower increases in flow rate as well as the backlashes against which the flow needs to be pushed. Therefore, the flow passages need to be designed so as to minimize the stagnation pressure drop in the system. Incidentally, it will also reduce the load on the fan and hence the power consumption. So this is a very important thing I'm telling you. You don't have to go too much deeper. All I'm telling you is the fan is trying to push some air, and if it has to push against higher back pressure, obviously it will spend more power and also produce much more noise. So you are losing both ways. The efficiency is reduced, at the same time noise is increased. And in fact, you will find most of the times a quieter machine is also a more efficient machine. Or conversely, I would say what they say, noisy machine is not only just bad for noise, it is also very inefficient machine. In fact, now talking on the lighter side, the person, for example, who shouts, he is definitely less, what should I say, wise in terms of decisions, because the two don't go together. The person who is relatively silent, he will make much better decisions. All right. Now, often the nozzles used in high pressure pneumatic cleaning devices produce high jet noise. This can reduce by means of specially designed multiple nozzles or bicycles. Let me see if I have slide here. Yeah. Now look at that. Whatever I am talking, I can explain some of those things. You see now, this is, let's say, a jet is coming out here, and this is the mixing region where most of the noise is produced. So you have around it a kind of acoustical shout. So net result is you are not disturbing that jet at all, but at the same time noise will be reduced. Okay, and this acoustical shout generally is portable. I can just tell you it's very simple. Like for example, first time I went to Agra, at the airport station. Very, very noisy. There was the AN-76 aircraft from Russia, and they were very, very noisy. And they had to be tested, and they wanted to demonstrate it to their air commodore. Okay. But oh hello, we just won't be able to hear anything. He was like, you can't explain anything there. You yourself can't stand, he will say anything yourself. They want you to explain the thing to their officer, their commanding officer, their commandant. So I just told them, I said, just make this portable, this acoustical shrouds and on a orchestral use. So because the whole thing was done separately in the hangar and moved in there, okay. And during the testing, the noise was much less, so you could talk to him with some effort and explain. But then they don't said, so we can't be doing this. I said you can because you are testing things in stationary system. So let this portable things be there. And they can use it. It's very simple. They're like, for example, in hospitals when you go and suddenly an emergency happens. So you find that people, some ladies, they will get together, their sarees, whatever, and then right there something can be done, and without anything, and then they don't move. So what I'm having support, these are very important things. I can give you another instance, which is like this earth moving equipment being used on the roads at night, for example. So you can have those portable acoustic barriers. Okay, put it during the day for the work, etc. And then you take it away, fold them up, put them in the truck, take it away. So that there is no permanent structure coming up there. So this is a very important thing. Portable mufflers, barriers, or shrouds. See the second one. Multiple jet nozzle or silencer. So instead of the jet is coming straight away like this, you let it go through this multiple jet nozzle. And you will find that because now a number of jets are coming out, they interact with each other in the shear layer, and net result is the noise, total noise produced is much less than what it would have been from a single jet. Another thing, highly porous plug or diffuser. You might have seen, you must have traveled by buses or trucks or whatever. They have this kind of thing because they are using air brake, okay, and they have very high pressure, and suddenly pressure is decreased, okay, and then so basically what happens, you let that air go through this highly porous plug or this one, and so basically inside very like 40, 50, 60 expansions take place, small expansions, and net result is what finally comes out. You just hear some, just a thing like this, and that's it. Otherwise, it will be heavy. So these are very much used under the contract. So you might have seen sometimes people are air brakes. Okay. Then this is, now look at this. This is something I want to show you. I was talking about bypass. You will see what we do. This air is coming, and you just put this one. So part of the air, it goes like this, and again mixes back. See here, comes out like this, and then mixes again. And net result is this is much quieter than it would have been straight. So here we are not doing anything extra. Same here, a part of the air takes this part, and again mixes. And whenever mixing takes place, it is an interaction of two free shear waves, and that is, that is actually it's a headache also, but at the same time, in this case, it really helps. One has to go into gas dynamics. Then only you understand, but that's not important. You can use the principle as well. Okay, we'll continue. Now this is another thing I was telling you, that we have very high pressure application, and I told you that the example I repeat maybe may not have attended the first day's lecture, second day. What I am trying to say is that in this particular application, this happened at Fertilizer Corporation of India, Sindri, and they had a boiler producing steam at 200 bars pressure. 200 bars pressure, and the quantity was 18 kilograms of steam being vented per second. And this is one thing very important. Please understand that if a boiler has to run started and it has to come to give you 18 kilograms per second at 200 bars pressure, it takes 48 hours to stabilize. 48 hours. So now let us say something happens. You don't need that steam. You can't say close the boiler. But 48 hours are gone. Okay. So you have to just vent it out. That's why the word vent. So what happens is, now when you vent that from 200 bars to 1 bar, pressure ratio is 200. It is hell of noise. So what you do is you make this expansion in stages. See here, it comes, this is that valve, butterfly valve, and then you have the first stage You have a number of poles here, and at the throat it comes down to 54% of the pressure upstream, and then again 54% here, etc. here, like that. And net result is that you have now, I am showing you 3 expansions, 1, 2, and 3. Okay. In that 200 bars pressure, you know our two is that much that it has a pressure ratio of 1.87 at the throat when the expansion takes place. So basically, you from 200 bars it comes to 110, 110 to around 60, 60 to around 35, 35 to 22, etc., etc. And finally, in 7 steps, I was able to bring it down. Net was a noise reduction of 55%. Now, this is all about I talked about control of noise at the source. Now, next is in the palm. For any existing noisy machine, the option of noise control at the source as well as designing a bypass is not available. The next option is to control the noise in the path, making use of acoustic barriers, hoods, enclosures, etc. for the casing related noise, and mufflers or silencers for the depth bone intake exhaust noise, vibration isolators to reduce propagation of the unbalanced forces to the foundation or support structure, and finally structural discontinuities or impedance mismatch to block propagation of the structural bone form. So I'm just giving you titles of each is separate book on each of this. Okay. This is regarding the past. Then now, the role of damping, particularly when you come to structure bone sound, or the noise that is produced as waves in the structures. Okay. Now, damper plays the same role in absorption of structure bone sound as acoustically absorbing materials does in dissipation of airborne sound. Now, see here, I have airborne sound and structure bone sound. And when I use reflective measures, for airborne sound, I use a sound barrier. For structure bone sound, I use a vibration isolator. Again, absorptive measures are for airborne sound, it's a sound absorber. For structure bone sound, it's a vibration damper. So putting it like this is very nice because all your concepts, they get verified. That why in particular situation we use this, other situation we use this. In practice, however, noise control measures are not purely reflective or reactive, not purely absorptive or dissipative. For example, a standalone acoustic enclosure consists of both types of components: impervious layer for reflection and acoustic lining on the inside for absorption, and similarly, viscoelastic pads combine elasticity and damping. Yeah, in fact, I will just spend a little time because there's many things that I have been talking. They will become clear. Please look at. Is it okay? Can everybody see? Good. All right. You see here now, my primary source is here. This is electric motor, which is running this pump. This pump is getting the liquid, the medium here, and then pumping it up to this here. So this is the operation. Now idea is to how to make sure that this operation doesn't make too much noise. So we start from the here now. First thing I do is I have the support. I must make sure that my electric motor or again which is there and the pump, they are supported in such a way that I have a single plate, a common plate supporting both the electric motor and the pump. And therefore you can see here, it may have to have different kind of surfaces to finally exactly bring the axis in the same line. And now whatever vibration takes place, whatever unbalanced forces come out of motor as well as pump, now they act on this plate, and from that plate we don't want this to happen, go to the ground, otherwise that will start moving the structure bone sound. So we use anti-vibration mounts. Okay? And this is whatever you study in vibration. So that is one thing. And secondly, damping is also included in this. So that when these vibration mounts use both. And not only that, you might have, if you have seen anti-vibration mounts, we don't use simply compression tension. We put it at an angle so that we also make use of shear. And shear is much more efficient damper than the simple compression. Alright. Now, please note here that this is coming here and it has to be supported, and this is what I have extended here. Whatever is here is here. And so this is called a pipe hanger. It is supporting like this, and then we have a sleeve, and there we have the damping gaskets. Okay. Then same thing here on the discharge side. Again you have one flexible coupling here and another flexible coupling here. So that any vibration of this should not be passed on to this, because if that happens, then that will go here and then put this valve into vibration. So it's very important that we make use of this kind of pipe hanger and this rib pad, etc. anti-vibration mounts, then flat pads, then metal spring, etc. Now, again, of course, if you see my book in chapter 3, all these things have been discussed in detail, and you have been told with respect to the natural frequency that you are taking care of, what kind of various kinds of vibration absorbers, what you can use, and also in terms of cost, in terms of the space they occupy, etc. But let me just tell you one thing, that if mass is more, that is a very machinery kind of thing, and you need good vibration isolation, the best thing is, please note, listen to this, best thing is metal spring. Metal spring can take much more load. At the same time, because spring has this, situation like this, the net result is that it is able to be more relative motion, and that's what we want. Okay, and that's why now you might have seen, if you look at the trains or locomotives, everywhere they use this kind of metal springs. Or you might have, if you look at bulldozers, or dumpers, again they use bulldozers. Everywhere you have, whenever you have more big mass, big forces to be taken care of, okay, then you use metal spring. Even bridges, under the bridges, for example, because you want that whatever is happening there, that should not disturb the people nearby, or they should not go to structures. So again, you use metal spring. And as engineers, you must be wondering, that how do you maintaining? Because once something is put, it is there forever. Okay, so you have to make sure that these springs are designed properly. And now let me tell you something interesting here. Please, everybody, what I am trying to say is, now in India, we have these springs with a minimum lifetime of 100 years. Because when you are putting those things under a bridge, now you cannot replace a bridge in the next 10 years or 20 years or 30 years. So it's designed for 100 years. Not only that, even for the cranes and everything else. So minimum is 50 years, because they don't design for more than 50 years, becomes very costly, and it's unnecessary because mechanical engineering keeps refreshing itself so fast that unnecessarily designing for such a long life has no meaning. Okay? Because any machine can be used for 10 years, 20 years, 30 years, not for 100 years. But civil structures, they have to be built for a long time. For example, how the bridge was built 150 years ago, it is standing there today, and it has to be standing for the next 100 years. So whatever we do, we have to really make sure that we use these principles in such a way that everything is taken care of. Now we talked first noise control at the source, then noise control in the path. Now I'm coming to the last one, noise control at the receiver end. This option is the last resort as well. The receiver may be protected from excessive noise exposure by means of earplugs or muffs, which are really actually popular to use. But anyway, they are easily available in the market. And then rotation of duties, like I was telling you, part-time removal in a noisy environment. So every worker, who works at a very noisy place, he works only for 2 hours in 8 hours. That's 6 hours. He's given duties which are invited. Then cabin for the operator, driver, or foreman, which is again a path control measure. So you have to give him a cabin because he has to be on the floor looking at what is going on in the workshop. At the same time, he also has to do administration, he'll be talking on the phone, etc. So he needs that. So when we give him a separate cabin, so that through the glass windows he can supervise what's going on. At the same time, he is able to carry on the work. The control room for the supervisory personnel in noisy test cells. This is a very important thing. For example, if you go to HAL or GDR, etc., where air engines are tested. Now, when an air engine is tested, typical air engine will be the size of this room. Okay, everything is put together. Now, you have to have a control room there, and then the noise inside is 135 decibels. Now, 135 decibels, let me tell you how big is the noise. If you are exposed to 135 decibels, you will actually feel as if somebody is piercing your ear with needles. That's the noise I'm talking about. It's that bad. Okay? So nobody will be there inside. The testing is going on. Nobody will be there at all. Everybody will be in their respective different cabins, but all part of the control. So they are there, and now that because I have designed those walls, etc. I designed that for 35 decibels. Okay, and then they were telling me, no, you have not done enough. You should have designed for more. But it's easily said and done. Because what happens is, when you design the walls in such a way that you get that much reduction, you forget that the noise has flanking transmission. Same noise will excite that wall is connected to something else, again connected to the room. So noise has different paths by which it travels. It doesn't travel only by the shortest path. So therefore, even though I might design for 50 decibel here, but other sources are such that suddenly doesn't go something more than 35. So this is another thing which is very important in the noise control measure designing, etc. That you have to consider all the paths by which noise can possibly travel from the source to the receiver. And finally, I want to tell you here, earplugs and muffs are readily available in the market. They provide an insertion loss of 5 to 15 decibels for the user, but then the user's functionality can be compromised. He or she may not be able to detect a malfunction in the machine, or may not be forewarned of the damages arising from a malfunction in the machine. So this is very important, See, when a worker is there and you give him earbuds, okay, now he's protected, but he's also having problems. If something goes wrong in the machine where he's working, he won't be able to detect that. He's not able to hear that. Okay? Or let us say something else happens there by which can threaten his life or whatever. He will not know because he doesn't hear that. Because he's so basically by doing this kind of thing, not from the receiver end, you are compromising his safety, his health, everything. So then coming back to that, I started the lecture with that. As engineers, we should always try to make sure that we design are quite simple. That's the most best thing we can do with least amount of money involved and maximum effectiveness. But otherwise, it's a problem. Now, We just compare the three approaches that I talked about and see where this is. Despite the cost disadvantage, noise is controlled more often in the path as a source because of logistic convenience and ready availability of acoustic enclosures, mufflers or silencers, or pressurizers. These are easily available. So most of the time, people use, they don't have the source option because they don't design the machines. Most of the time, you go anywhere, machines are already bought from somewhere by somebody, etc., etc. And so that option is not. So you only have the next option, designing path meshes, and that is what I am saying here. So it's relatively costlier, but still it is done because that is easily done. Because you have the silencers, mufflers, vibration isolators also available in the market, or you can easily design it yourself and use it. So that's what is done. Right. The noise control at the receiver end, they protect a particular receiver from the noise, but would not have others. See, I was telling you that if a machine is noisy and you give this worker earphone, he's protected. But how about the person standing nearby? You know, he's also getting the same noise. His own machine is not making noise, but he's getting this noise. So you have to give earmuffs to him also, or everybody around. So that's what I was telling you yesterday, that one of the important things to remember is that you design the whole workshop properly. Like that is when I am approached by this kind of problems, I said no. Give me the complete chart. I'll design the complete layout for the machines, and then you will not have most of the problems. Don't say that everything is given, then do something. That's not cost-effective way of doing it. Okay. So noise control at the receiver end may protect a particular receiver from the noise, but would not help others. This comment would also apply to some of the path control measures. Therefore, the noise control at the source or designing for quietness is the most cost-effective way that will help everybody in the vicinity, not just operators or drivers of the machine. Now, this was always otherwise, but here now, what happens is the facility is already there. All those options I am talking about, they are not there anymore. There is a already existing facility, it's very noisy and you have to reduce noise. So what do? If there is a complaint about environmental noise due to an existing facility like captive power station, compressed air facility, or a large HVAC system, or a workshop, we may proceed as follows. These are the steps which every noise control engineer will have to follow. First is, he has to make sound pressure measurements so as to identify and rank orders different sources of noise. Then calculate the extent of noise reduction required for the noisiest of the sources the machines are processing in order to reduce the total noise in the neighborhood to the desired level. Then identify the paths of noise transmission, vector-borne as well as airborne, from the major sources to the neighborhood and plan the path control measures. Then estimate the cost effectiveness of different alternatives. Then carry out detailed engineering and installation of the selected noise control measures. And finally, verify the effectiveness of the implemented measures and work out refinements or corrections if as necessary to meet the environmental noise levels. So as you can see here, it's a complete set of measures, which need to be done if there is already an existing facility which is noisy. Therefore, again, coming back to that, I say to myself, I should be allowed while designing the facility, right at the beginning, rather than giving me an existing facility and then say do something. Now, this is where it comes in. What is important is environmental impact assessment, EIA. All of you please remember that when you want to put up a new factory, it needs clearance from the Ministry of Environment and Forest, which means the Central Pollution Control Board or the Tamil Nadu State Pollution Control Board, etc. And they will ask you, have you got an environmental impact assessment done? If you have got it done, shows, otherwise you cannot even apply for a clearance to certain object. And now EIA is done not only for noise, it's done for air pollution, water pollution, ecological effects, etc. Okay, so everything has to be taken care of. Only then it is. So this is one thing I want to share with you, that earlier only air pollution was a problem, or earlier only water pollution was a problem. Then ecology came, and now noise is also a part of it. So this discipline of noise and vibration control has to be introduced in mechanical engineering, because all of you as engineers, you will, like or not, you will have to tackle some of these problems. Okay? And that's why I was telling you that DST commissioned the book. They gave me all the money for writing the book, etc. They gave me also money to run the courses. I've been training teachers in different places of the country. All money comes from DST or CRP. Okay, and they are doing this because all teachers need to be first trained in this field, so that they can start a active course for undergraduates, third year or fourth year, noise and vibration control. And that's how it is. And that's why this book is written in such a way that minimum mathematics, all usable material as I'm presenting here, and that I'm sure it can be. I think I'm not going for this because now it comes to design of acoustic enclosures and things like that. I don't know, do we have time? It's 12:30. I have slides, I don't mind, but you ask yourself, you have time?
We'll close then.
Huh?
We'll close.
Yeah, so then let's close it. Thank you so much.
Thank you, Professor. Students, if you have any questions, please do come forward. Any questions?
Everybody has understood everything.
Students, come forward.
Sir, my question is just simple, sir. In olden days, they had used bells for acceleration, sir, that used to make so much of noise. But now in electric vehicles, what are they using, sir?
In what?
In electric vehicles, now in electric vehicles, what type of bells are used for acceleration?
What type of drive system is using actively?
See, basically, you are using motor as the power source, okay, electrical. And now, from there now you have to take that drive onto the wheels. So, now two things are there. One is that, taking the power from one source to another. But more than that, what happens on the way? Because the ratio is very high. There is a motor running at 3000 RPM, and finally at the wheels, it is maybe 100 revolutions per minute time. So this is very high reduction in this speed. But second thing is, this is also, you have to run it at different speeds. And every time you cannot instantaneously change the speed of the motor. So theoretically it can be done. No, but when you are, taking the power of something like 100 kilowatt and doing it, and suddenly you can't say that I don't want it, so it change it. And imagine as a mechanical engineer, the industrial loads, the stresses that can happen whenever you do sudden something. So then, because you have to have gear systems or transmission, that's there. In fact, the biggest problem in the whole electrical vehicle is design of transmission. All noise also comes from transmission. Our failures also happen there. Everything transmission has become electric vehicle. That's a field in itself. So that is how it's done. So essentially, for example, I will go for let's say belts, etc. But belt, of course, has one very good advantage that it gives me damping. It also increases the surface area I was talking about. So therefore, it is much less noisy and all that. But then it has other problems also, because suddenly something has to change. It cannot do. So basically, it has inertia as well as damping, and the way it's holding on to the pulleys. So that comes into this. So it's very quite complicated. Because I have not worked on it, so I can't go deeper than that. But main problem is, or main challenge is transmission.
Thank you, sir.
In fact, I like to tell you here, because it is now clear that in the next 10 years or so, most of the automobiles will go to electric vehicles. Okay, so in your colleges also now you have to look ahead and introduce electric vehicle and all technology that goes with electrical vehicles. That's very much part of mechanical engineering. In fact, I can tell you firsthand, because I have been consulted to several companies, basically who dealt with internal combustion engines, and all of them are changing over. So in fact, often the joke, that your next generation will not know that we have problems like these popular silencers, etc. Because the whole thing may become obsolete sometimes. So all of you now start thinking, all your designing, research, development, everything should move towards electric vehicles. Yeah, now you
Sir, I have two questions. One is related to your slides, and the second one is not related.
ask one at a time.
The first one related to your slides. You spoke about environmental impact assessment.
Yeah.
What is the role of students? Can students carry out this?
Oh, very much. In fact, all like the EIA that I have done, I have only done through my students. I couldn't have done myself. The kind of total work that is involved, it needs several hands. For example, I understand the city. I'll just tell you. This in Kottayam, in Kerala, there is a rubber board. Rubber board is basically central board. Headquarters are in Kerala. Okay. And they wanted to put up what they call a model rubber wood factory. Okay. And now naturally, noise had to be controlled right at the designing, not even at the source, at the design. So they asked me to do an EIA of a factory which has yet to take place. Okay. And when they first came to me, I was wondering where do I start, because I had no experience. But as I've been doing it always, I take up everything that comes as a challenge. And all I did was, I involved 3 of my AICTE students, and they did it part of the project. So what we did was as follows, and please you listen, because this is how EIA is done, so I'm giving the procedure. We asked the factory people, designers, that okay, what are the processes you'll be doing for cutting rubber wood, etc., etc. And what those processes will involve, what machines will involve. So that was easy, because after they were not doing anything from scratch, they already had a model factory in some other country. So I said, okay, show me for that country what all they are using. The next thing I did was, I said, out of this, you tell me what machines you are going to use. So we picked up that and then made another drawing where we had it. Now, now I wanted noise levels. So we got noise levels partly from the same company. They had bought machines from some companies, and those companies had the noise levels. You know, there everybody has to have. They cannot sell without this noise levels. So I took up those manuals, and then I knew that now this much noise will be coming from here, this one from here, and all. So now, then I put all those things as black boxes on a page. So whole factory I designed purely conceptually first, such that how the process, the things will move, they should move in proper way. At the same time, noisy machines or very noisy machines, I should be able to isolate them. Okay, in the flow of materials. And then next thing was that we put a hypothetical shed over it. Okay, and then we found out, what is the noise level that will be generated in each machine, and anti-graphically adding the way I was telling you yesterday. Okay, and then we said, all right, at that window, that place, it is so much there, it is so much there. And then we also compared in what kind of area that factory is going to put up. Okay, and it was a that whole Kerala is like that, but anyway, it was almost like a forest area. Okay, so we had to apply those conditions of real quietness. Okay, so let us say I get that 100 decibel at that point, and I find that nearest residence will be at such and such a distance. So then I find out this noise going from there will be how much at that house. So that I came to know what are the kind of reductions I need. Okay, so in this way we, this is not an impact. So we assess the impact of the factory, what it would be if we don't do anything. Then we start with the next step. Next step is that, okay, if I put this wall with a noise reduction of minimum 20 decibel, then what will happen? Or on this side, I do only 15 decibel to this one. Because we don't want to overspend. The idea is to do what is just necessary. So we did all that, we put those reductions, okay, and then recalculated. And that's why I was telling you I needed students, because a lot of work had to be done. Okay, because they had almost like 25 to 35 machines, and we had to do for each machine frequency levels, different output bands. So tables and tables of work. So in fact, there was enough material for MTech thesis of 3 MTech thesis. So there was no problem for me to justify that there was enough for the getting. But anyway, it was a good learning for me also. So then what we did was we further tried to play with various alternatives. Alternatives I can explain. For example, instead of putting one big machine, if I do the same operation by 2 parallel machines, or say a material that is coming, again, instead of moving only in one path, it moves in 2 or 3 different lines. What will be the extra cost or what will be the reflection? So this is how we went on and on and on. And finally, we were able to give them a complete sketches of those. I mean, they have to then buy machines, etc. We had to follow later. But we did all that and made a report. In that report, we indicated that even after doing all that, out of that 25, 2 machines had to have their own extra, what we call acoustical enclosures. And they were not easy to design because enclosure cannot be just enclosed into material, it has to move. It has to get some operation done, it has to get out. Every opening that I give for material to move, I am giving chance for noise to get out. And again, I have to take that into account. So that kind of learning, I would have not got for anywhere else. Because all our knowledge was tested. And finally, we gave that report saying that noise will be within the limits that prescribed in the environment, provided these two machines are separately provided externally. So they got a clearance from the Central Pollution Control Board with the same thing. Condition was that if these two machines, they will be provided this one, only then they can start operating. So there are two steps. One is that the Pollution Control Board first allows you to go ahead and gives you only conditional clearance. You're provided you do what your consultant has told externally. Okay. So after the whole factory came up, they were not allowed to start manufacturing straight away. Again, I was called, and we had to now do what we call dry run of the factory and find out actual noise levels. And then those things were done on those machines. Finally, when everything was done, then I had to give the second report that I'm satisfied, this is it, etc. And then only they started. Now that has really become model rubber factory, because their environment-wise, it's not only satisfies the noise limits, also air pollution limits, water pollution, ecology, everything is taken. So in a way, Central Pollution Control Board also was very happy, because they needed a factory in the country which can be model for others. Otherwise everything remains on paper. So this is what we did.
Other question is, tell us something that you learned or wish you had as an North Indian you learned from South India. What did you learn from South India?
Oh, lots of things. I just want to tell you that they have opened up a non-technical but very important subject. Listen. If you look at the history of the country, Punjab was attacked again and again and again, right from Alexander the Great. First those people Greeks and then Turks and Moors and this and all that. So net result was that those people only who could sort of fight back, only they remained. Others kept moving out. Either the east or south, all peace-loving people came from the south or east, etc. Because they just don't stand that kind of thing. But on positive side, those who stayed out, they were real fighters, not necessarily fighters in a physical sense. But for example, I was telling you that when we came as refugees, all the data showed that the way those refugees settled themselves, how successful they became, and in fact, I think USA also to see how the all Punjabis, maximum will be those refugees who had come from Pakistan. They were real fighters. Okay. So, so whole a new kind of race developed. And that is what also helped in a different way. For example, in the country, we have only 2% 6, urban 6. But then others are not very urban, otherwise they are also similar kind of factors. So, there are only 2%. But in the armed forces, the army, maybe 25% are Punjabis. Okay, so the country really got defenders, for this one. So now, let me come to your question. When I came to South, it was a big cultural shock. It was a big cultural shock, but everything was so very different. In fact, first one thing very pleasant I had, I was traveling in the bus, and inadvertently I stepped on somebody else's foot. So before I could say sorry, he said sorry. And he touched my this one. I just don't believe. in Punjab, I would have been slapped even before talking. You know, because people are extreme, temperamentally, they are extremes. If they love you, they can die for you. And if they hate you, they can kill you. So but I'm just using word, please not take literally, but I'm only saying there the temperament is extreme. That is love or hatred, both they can't control. Okay? So but then, you know, I really realized that because I settled in Karnataka, I've been there now more than 60 years. You know, that the Kannadigas were really very different kind of people. Much more tolerant, you know, much more understanding. You know, anytime you something like that happens, other person apologizes that he touched you. You know? So this really taught me, that there is another way of living. And that really changed me completely. In fact, let me also tell you the negative side, that now when I go to Punjab, they don't consider me Punjabi at all. They say, you are spoiled. According to their definition, I am spoiled because I am no longer Punjabi. Because I don't have those kind of tendencies, which I would have had if I continued. So this is general thing I am asking, but after we can stop later. That is what, in fact, it's very good actually that, this kind of thing over the last thousands of years happened automatically. Some kind of people moving to one region or there and then stopping, etc. So that was a very nice thing that happened, particularly to Punjab, because the same fighting spirit also comes out in working. They work very hard. If you see a Punjabi farmer, his productivity is much more than what you have here. The man at 3 o'clock gets up and does everything, and like after 6 o'clock, and then he takes a breakfast which you wonder as how can a person eat so much. But then he takes and he digests it. Okay, so whole thing is that kind of thing. I feel that it's good for the country that how they could so few people in Punjab produce so much wheat that whole country was being fed at one time only Punjabi wheat. And they are so hard workers. So anyway, so general thing. Thank you.
Any other questions? Thank you. Successful people don't wait for the opportunity to knock, but create the opportunity on their own. Dr. Manohar Lal Munjal, Professor, INSA Honorary Scientist, Department of Mechanical Engineering, Indian Institute of Science, Bengaluru, serves as a great example to the court. Over the last 5 days, we have had deep insights into several issues. Dr. Munjal taught us several best practices of dealing with our emotional self. And he inspired us a lot with his life story by explaining this principle of mastermind at work. No matter what the topic he touches upon, he never failed to inspire us. Hope everyone